For section 3.2, polynomial functions of higher degree, continuing with that, we're going to talk about the graphs of polynomial functions. So many basic features of polynomial graphs. So one, they're continuous, meaning no breaks in the graph. What that should mean to you is from left to right, no matter what you're doing with the graph. If you put down your pen, you should never be, pen or pencil, you should never be lifting it. Okay, it has no breaks in it. You wouldn't be crossing a hole, you wouldn't be crossing an asymptote, anything like that. Okay, so they also have nice, smooth, rounded turns, right? Like I just drew. There would not be anything such as that, a sharp corner. That would not be a polynomial graph. Okay. The degree of the polynomial, the highest power, determines the basic shape, whether it's kind of U-shaped or S-shaped, which we'll talk about. And the leading coefficient, whether it's positive or negative, like we've talked about several times, determines your end behavior, okay, if this thing is kind of going up or down. All right, so let's talk about some basics of some basic graphs that you know, all right, just to kind of get you thinking about what we're talking about. So in a line, let's just say y equals x. Your a value in front of x is positive. I don't care what number it is, but it's positive. That should mean it has a positive slope. Likewise, if it was y equals negative x, if the a value is negative, it goes down from left to right. Okay, nothing new. In a parabola, if a is positive, same thing, you know, based on the shape that it's U-shaped and it opens up. That would be like y equals x squared. All right, so I went back and added that in. So y equals x squared, if a is positive, it opens up. And like you know, if y equals negative x squared and that a value is negative, then of course the parabola opens down. Now, what we're going to say here, guys, is memorize the a equals positive patterns for end behavior. And then if it's negative, just flip it. Okay, change it. Just do exactly the opposite. So in other words, y equals x cubed. We've seen that. We kind of call that S-shaped. We know it could look like this, but the cubic should tell you that it could cross the x-axis and have up to 3 roots. So it could also look like this. What we're worried about, guys, is the end behavior. We're talking about these arrows at the end, okay? So imagine you're standing in the middle, if you will. I'll just put a dot here. If you're standing in the middle of this or the middle of this, and you're looking at the end, just the arrow, that's what we mean by end behavior. So if you're looking to your left, I hope you would tell me that this graph falls to the left. And I hope you would tell me it rises to the right. Okay, those are words that are going to be important for some district testing that we will have to do this semester, or it'll probably be maybe next semester also. So falls to the left is definite lingo we want you to know, and then rises to the right. Okay, so again, let's look at just the positive a behavior for like x to the 4th. So x to the 4th then would be back to, it could look U-shaped, okay, with something going on that you don't necessarily notice. Or if it's going to cross up to 4 times, if the x-axis was going through there, it could look like that, okay. Again, place yourself in the middle, pretend you're there or there, and talk to me about the arrows. Okay, what do those arrows do? So to your left, the graph is at the end, not immediately to your left, but the arrow is doing what? Well, it should be rises to the left, and it also rises to the right. Okay. Now let's talk about some patterns. How many roots, x-intercepts, zeros, solutions could each of these have? So this is a keyword, could, like we just talked about. y equals x to the fourth, we just talked about over there, the one that kind of looks like the W, could have 4 roots. Y equals x cubed, the first one above, could have 3 roots. Well, now we also like to ask you about how many turning points could each have. Well, look above, guys. If I follow the, let's give us a little more room. So let's talk about the y equals x to the fourth and the y equals x cubed. All right. So if we're talking about how many turning points could it have, well, in y equals x to the fourth, how many turning points do I have? Meaning, where do I switch from coming down to up? That's 1. Up to down, that's 2. And down to up, that's 3. Okay, from what I have above. So if it's x to the fourth, then I could have up to 3 turning points. Look at the cubic. Okay, go with the one with the max turns. So how many changes from up to down or down to up? Well, I could have 1 here, up to down, and 1 here, down to up. All right, so if it's a cubic, then I could have 2 turning points. All right, so is there a pattern forming there? Well, hopefully you're seeing that the degree of the polynomial is the same as how many roots it could have. And the turning points is always 1 less. Okay, that would be the pattern that we are looking for. So if I was asking you then to sketch y equals x to the fifth. Let's notice the pattern, guys. Look at x to the first. The right one is going up. X squared, the one on the right, is going up. X cubed, the one on the right, is going up. X to the fourth, the one on the right, is going up. So I'm comfortable saying that if a is positive, the one on the right is always going up. Okay? It seems to be the one on the left that's always changing. So notice, when it's back to the line, when it's to the first, the left side is going down. When it's second, it now goes up. When it's third, it goes down. When it's to the fourth, it goes up. If you're memorizing that pattern, okay, and I usually like to have you guys use your arms, okay? If you put both arms up, pretend you're a parabola, drop your left arm down, you're now the shape of a cubic. Put your left arm back up, you're now x to the fourth. Put your left arm down, you'd be x to the fifth. Put your left arm up, you're now like x to the sixth. Okay, so if you get that pattern memorized, then if I ask you to give me a quick sketch of x equals y to the fifth, then you should be telling me that I know it's going to possibly cross 5 times, have 4 turning points, and the right side goes up and the left side goes down. That's what you should memorize, is the pattern, so that if I now ask you to sketch y equals negative x to the fifth, I don't jump straight to that. In my mind, I am sketching y equals positive x to the fifth. And then negative x to the fifth, again, to make it smooth, think about the curvature of it. It would now have to look like this. Okay. All right. The leading coefficient test. So remember, arrange your terms of polynomials in standard form, descending degree of the exponents. That's what we're talking about. If the highest power is odd and the leading coefficient is positive, then the graph rises from left to right. Okay. Right, so it'll go up the entire time. If the leading coefficient is negative, the graph falls from left to right, such as those two. If the highest power is even and the leading coefficient is positive, then the graph rises on the left and the right. Both sides go up. These are just the same patterns we were just looking at, just said in a different way. If your leading coefficient's negative, then your graph falls on the left and the right. Both sides are going down. Why do we have the dashed lines? Because remember, it could be just going straight across, or maybe it's doing something like this. Okay, we're just saying we don't know what's going on in between, but that's what's happening. Okay. All right. So let's look at some examples here. Determine the end behavior for the graphs of the following functions. Okay, so first things first, I'm going to follow my procedure of putting this in standard form. Highest degree in front. So rearranging this is negative 3x squared minus 7 halves x plus 5. And I don't care how much is written there. The only thing I'm worried about is that leading coefficient in front of the x squared. It is negative. Okay, so I know for an x squared that if it's negative, both of the arrows are going to go down, right? And then we can just say, yeah, I mean, we know it's a parabola, but we can say something's happening in between that looks roughly like that. And so now we can describe it. We can say it falls, if I was standing in the middle, think about it that way, falls to the left and falls to the right. All right, next one, it's already in standard form. Cubic is either going to look like this or this. I don't really care, either one. If I'm standing in the middle, if you're determining the end behavior, you're going to tell me if you were standing in the middle and just looking at the end, it falls to the left and it rises to the right. Okay, so hopefully that's pretty straightforward stuff there. All right, so now these, let's say sketch the graph of y equals x to the nth power and the specified transformations. Okay, and then let's describe them. All right, describing them is what we're going to do. So if our parent graph is y equals x to the fifth, right? You should have in your mind what that looks like real quickly. All I care about is the end behavior. So I know my arrow goes this way and this way. Because think about that's the only way that they could make a nice smooth curve in between them. Okay, right? If you kind of think about like this. So it would have to curve that way. All right, so usually what you will see on my paper is I will just draw those arrows. Okay, that's just kind of getting myself set up. So I know x to the fifth has that curvature, and that's my end behavior. So for f of x equals x plus 1 to the fifth, you should be telling me it shifts left 1. Okay. For part B, x to the fifth plus 1 in a different spot should shift it up 1. All right, C, probably want to put it in the right format first. Descending order, negative 1/2 x to the fifth plus 1. So now I know the x to the fifth term wins out. The negative 1/2, well, let's talk about what the 1/2 does first. So if you're multiplying your x values by 1/2 to get the y or the h of x values, hopefully you're thinking that makes it wider, it shrinks it vertically, whatever wording you want to say. So I'm going to say shrinks vertically. And the negative is going to make my arrows turn this direction, if you will. Okay, that's because of the negative in front of the half. And what's the 1 going to do? And it's going to shift up 1. Okay, all of that would be a good description of what's happening. So why don't you try D yourself? All right, in D, first things first, order of operations inside the parentheses would first shift this thing left 1. Okay, and the 1/2 is going to say it shrinks vertically. And the negative in front of the 1/2 is going to make my arrows for the end behavior look like that due to the negative. Okay. So remember, on my paper, I usually describe to you what's happening and kind of show you the work of what's going on. You always have the graphs in your workbook already worked out for you. Okay. All right, next, zeros of polynomial functions. So the zeros of a polynomial function are the values of x that are solutions to f of x equals 0. The real zeros are also called the x-intercepts. And as you know, a function can have no more zeros than the number of its highest power, right? Such as a quadratic equation, x squared, can have at most 2 real zeros. A cubic, x cubed, can have at most 3 real zeros. And also, a polynomial function of degree n will have at most n minus 1 turning points, right? We saw those patterns earlier. Turning points are the points at which the graph changes from increasing to decreasing or vice versa. And for this example, then a quartic x to the 4th will have no more than 3 turning points in the graph. Okay. That's just written out of the exact same patterns we worked with earlier in the notes. Okay. Other methods will be used later, guys, to find zeros. For now, most of them can be found using factoring. And repeated factors lead to the repeated zeros or the double roots that we have talked about. So let's work with this. For example, let's find all the real zeros of each function. Okay. So if I'm finding all the real zeros, that means where that equals 0. You're trying to figure out what x's would lead us to that. So that does factor into x plus 2 and x plus 3 equals 0. And therefore, x would equal -3 or -2. Okay. 5, if we're going to factor that one, try it yourself. Hopefully you're taking out the GCF first. And setting the g of x equal to 0. Quadratic type, right? So x squared goes in the front of each because of that middle power being half of the original power, the x to the 4th. Now I'm just worried about the numbers that give me the 1, and the -6 numbers to work. Let's see, -2 and +3. That looks like that would work. Okay. We said in previous notes and previous talks, I can force anything to be difference of perfect squares. So I'm okay to think, and I'll emphasize that again. I'm okay to think about factoring it this way, as long as I don't actually give factors with end results this way, and we'll talk about that in a second. So difference of perfect squares for x squared minus 2, right? The square root of x squared is x. The square root of 2 is the square root of 2, and make 1 plus and 1 minus. Okay, that's great. I like to think of it that way because then I don't accidentally forget my plus or minus if I were to extract square roots. Okay, and then x squared plus 3. Remember, we've talked about factoring the sums of perfect squares. It can happen if you have imaginary numbers. Okay, so that could be, but please notice the directions. It says real. But if it did not, remember that could be x plus root 3 times I and x minus root 3 times I. Okay, but since it says real, I'm going to skip it. I'll just leave these as they are. And the reason I like to think about this again is this is now nice and visually easy for me to see that x equals 0 from the first x, negative root 2, and positive root 2. Okay, the x squared plus 3 just doesn't produce anything because it's imaginary. So why again did we say think about that? Remember, factors are what's in parentheses. And so we say that because technically, because eventually you'll be giving me some factors, technically factors can't have roots. All right. Roots. I'm having a problem with this one. I'm trying to talk about the root symbol. So roots or imaginaries or i's in them. Okay, that's just technical. So you won't ever give me a factor with those in it, but if I see it in your work, that's beautiful. That means you're totally thinking along the right lines. Now, what if I asked you to find the polynomial function that has the given zeros? Now think about that. Isn't that just reverse of what we did above? I'm giving you the answers that are boxed, and I'm asking you to work up, okay, if you will. So if I knew that x equaled, for instance, let's get a little more room. If I know x equals negative 3 or x equals negative 2, well, turn those into factors, which means basically set them equal to 0. So bring those back over here. Now put them next to each other. It just says find a polynomial, meaning I can call it anything I want. It could be g, it could be h. I'll have x plus 3 times x plus 2. Go ahead and multiply them out. This is what we're looking for when we ask you to do this. We'd have what, x squared plus 3x and 2x, so 5x plus 6. Okay, and that is my final answer. Okay, notice it's the same as we had above in 4. Okay, so that should go together. I will say, however, there's actually multiple correct answers. Okay, and we'll talk about why for a second. Now, I want you to just give me the basic one like this. Okay, don't get fancy. Sometimes that can get you in trouble. But just so you understand, you could have been multiplied by a constant. It could have been multiplied by a constant. And that could be any constant, which means there's an infinite number of solutions here. Like, for instance, couldn't g of x be 2x squared plus 10x plus 12? Because wouldn't that result in you taking out the 2 and you'd be back to the x squared plus 5x plus 6, which would yield still those same solutions of x equals negative 3 and negative 2. Okay, so that's just a side note. Multiple answers. Again, stick with just the basic one. Don't try to get fancy. Sometimes it backfires. Right? So why don't you try this one for yourself? Find the polynomial function that has, 3 given zeros. Okay, and come back and join me. All right, so if x equals 0 or x equals negative 2 or x equals 3, I'll just call it f of x this time. That means x is the first factor, x plus 2 is the second factor, and x minus 3 is the third factor. Easiest to leave the x alone and probably distribute the two binomials to get x squared minus, well, minus 3x plus 2x would just be minus x, and then minus 6, and then distribute your x. So x cubed minus x squared minus 6x. Again, that's the answer I want from you. Don't get fancy. Could it be multiplied by any number? Sure. Okay. All right, see what you can do with that stuff.